Hey y'all, welcome back. On today's lesson, we are going to continue to talk about separable differential equations. The ones we'll look at today are just maybe a slightly more complicated than the ones we looked at in the first day, but the overall process of finding y is going to be basically the same. We're still going to try to separate out our x's from our y's. We're still going to integrate both sides and then try to find c to get the particular solution. But on the ones that we're going to look at today, they're just going to be maybe a little bit more complicated than what we've seen on the last day's notes and homework. We're also going to talk briefly about slope fields. So this is going to be a new concept that we're going to touch on. We're not going to get too deep into it. So let's get into these differential equations. The first one says, consider the differential equation f prime is cosine of 3x over 4 f of x. Let y be the particular solution to this differential equation with the initial condition that f of 0 is negative 2. So one note right off the bat is that when you see this f prime, just know, we've talked about this before, but this is just a different notation. That means dy over dx. So all the problems that we saw last time had the dy dx, or I think most of them did anyway. I don't think we saw one that intermixed the two notations, the Lagrange notation with the Leibniz notation, but you should know at this point that those are the same thing. So if we want to start to try to find y here, try to find that function f of x, we need to separate the x's and the y's. And we could do that by using that cross products property. Now, we want to be careful here because we want all the x's to be in term on one side. One thing that might throw you off here is the f of x that we see in the denominator. You might think that that needs to go with the x's, but even just immediately after saying this equation, it says that y is f of x. So a much easier way to approach this is just like, don't even think about it as f of x, just think of it as y. And when you regroup them, when you separate out the x's from the y's, you're going to have that f of x listed as a y. Actually, let's just go ahead and rewrite it. It might be easier, instead of just trying to do everything in our head here, to just rewrite this equation so that it looks more like what we've seen already. Dy dx is cosine of 3x over 4y. Okay, so now it looks a little bit more obvious, I think, how we're going to work this one out. First, we'll use the cross products property, and we'll get 4y dy equals cosine of 3x dx. And we do need to integrate both sides here. So we're going to integrate the left-hand side. We're going to integrate the right-hand side. And the left-hand side should really give you no problems. Okay, we're just going to use that anti-power rule and increase that exponent by 1, divide by 2. 4 divided by 2 is 2, so get 2y squared. We know we're going to end up with a c, but we can always throw that in on the end. So 2y squared is going to equal, and then we have cosine of 3x. This is where you got to kind of go back and remember that we sometimes have to use a u substitution. So I'm going to let u be 3x, and if that's the case, then du is 3dx. And since I don't have the 3dx, I just have the dx, I need to divide both sides by 3, so 1/3 du is dx. So I can rewrite this as 1/3 times the integral of cosine of u du. And this becomes a much easier integral to handle. That left-hand side is kind of already taken care of, so I just have 2y squared equals 1/3 times the integral of cosine, which at this point, hopefully you've got that memorized, is sine u. And of course, we got that plus c that we've already implicitly combined with the other one, so we'll just leave it like that. Now, the only thing left here is we do need to go back and replace that u with 3x, so I'll do that now. 2y squared equals 1/3 times sine of 3x plus c. Now, we do need to use that initial condition, that f of 0 is negative 2, to find the c, so that we can find the particular solution. Before we do that, we still need to isolate y, though. So I need to divide both sides by 2, and that'll give me, let's see here, y squared equals 1/6 sine of 3x plus c. And then I want to take the square root of both sides. Okay, so I have the y equals, we would get a plus or minus because the square root of y squared is absolute value of y. We get a plus or minus square root of 1/6 sine of 3x plus c. We need to find that c. But something else we need to do here is choose whether or not we want the plus or the minus. And the way we make this choice, do we want the plus or the minus, is based on that initial condition. F of 0 is -2, so the output must be negative, meaning we are going to disregard that positive sign. So now let's go ahead and find our c. Using that initial condition, that f of 0 is -2. So -2 will be our y. So we have -2 equals negative square root of 1/6 times the sine of 3 times 0, which is just 0, plus c. We can get rid of the negatives because we can divide both sides by -1. So 2 equals the square root of 1/6 times sine of 0. So sine of 0 is 0. So that works out pretty nicely. It's just going to be times 0 plus c. 1/6 times 0 is 0. So really you just get 2 equals the square root of 0 plus c. Squaring both sides will give me 4. So we get 4 equals 0 plus c is just c. So we got c is 4. And now we can write our final equation here. Y equals negative the square root of 1/6 sine of 3x plus c. So we did need to do a little bit of u substitution in there. Anytime you've got a composite function that you need to integrate, most likely you're going to have to do that u substitution. Number 2 says, is y equals e to the 5x plus 8x minus 5 a solution to the differential equation? Okay, now this can be a little tricky because we really haven't solved a question that's worded quite like this. But what we can do is we can actually just test by substituting y prime and y double prime into this equation. And obviously we're going to need to find y prime and y double prime. So if y is e to the 5x plus 8x minus 5, y prime, the derivative of that, would be e to the 5x, and then using the chain rule, we'd multiply by 5. And, maybe it'd be easier to write that as 5e to the 5x, but I'm just going to leave it like that for now. Plus 8. Yeah, that's it. So I think I will rewrite that. I think it might be a little easier to look at if we put that coefficient out front and just kind of write it like this. So this is my y prime. Okay, and we're also going to need y double prime. So we're going to need to differentiate that one more time. And we will differentiate, I think, this guy right here. So the derivative of 5 times e to the 5x would be 5 times, e to the 5x, but times another 5, plus, then the derivative of 8 is actually just 0, so we're not going to add anything. So y double prime will be 25 e to the 5x. Okay, so that's my y prime and y double prime. And so we're going to test, it's just asking if y is a solution here. And it's kind of the implication being there might be multiple solutions, which of course there are because we have the plus c's and all that. But so yeah, to test to see if this works, we are going to just simply substitute in this expression for y prime into y prime and substitute the expression for y double prime into y double prime and see if it all works out. Hopefully it does. Well, I guess we don't really hope that it does. We're just trying to see if it does. I mean, the answer might be just no, that it's not a solution. So yeah, let's see what happens here. So 5 times that y prime, okay, which is 5 e to the 5x plus 8, it's the y prime, minus y double prime, which is 25 e to the 5x, minus 13. Does that actually equal 27? So let's see. If I distribute that 5 on that first expression, I'm going to get 25 e to the 5x plus 8. Ooh, I like where this is going. E to the 5x minus 13. And does that equal 27? We still don't know yet. But we do have 25 e to the 5x minus 25 e to the 5x. That's just going to equal 0, right? Oh, wait a minute. Hold up. Mr. Schuler, you made a little mistake here, but it's not too grave of an error. I mean, it is an error that'll get my answer wrong, but it's going to be an easy error to fix. When I distribute this, 5 times 8 is actually going to be 40. So let's fix that. There we go. Okay, back to what I was saying before. 25 e to the 5x minus itself is just going to be 0. So that leaves me with 40 minus 13, which does in fact equal 27. Okay, so our answer is yes. Yes, y equals e to the 5x plus 8x minus 5 is a solution to the equation 5y prime minus y double prime minus 13 equals 27. Number 3 says consider the differential equation. Let y be f of x be the particular solution to this differential with the initial condition that f of negative 1 equals 2. Part A says write an equation for the line tangent the graph of f at x equals negative 1. Then use your line to approximate f of negative 0.9. This is going to be another one of those questions where we use a linear function to approximate the value of something that might be a bit more complicated to compute by hand. So whenever we're trying to find the equation for a tangent line, we want to use that point slope form. So we're going to need a point and a slope. And ultimately, we're going to write this equation in the form y minus y1 equals m times x minus x1. Now, the point that we're going to use is going to be the given point. Okay, it says f of negative 1 is 2. So that's going to be my point. The slope, I'm going to have to calculate using this slope equation. Keep in mind that dy dx is simply the slope of f of x. So the slope is negative x, in this case negative 1. So negative 1 is actually going to end up being positive 1 times y squared. Now y is 2 here, so 2 squared is 4 over 2. Now 4 divided by 2 is 2, so my slope is going to be 2. Now I'm ready to write my equation. Y minus 2 equals 2 times x plus 1. Finally, we're going to use this linear equation to approximate the value of f of negative 0.9. Notice how we haven't even found what y is. We're still able to approximate values that are around a given point. And that's really the value of doing what we're doing here, finding linear equations to model something that's a bit more complicated and allow us to evaluate or at least estimate the value of a function that we don't even know what it is in an explicit form yet. So anyway, we'll evaluate f of negative 0.9 by substituting in negative 0.9 into x. Negative 0.9 plus 1 is positive 0.1. So we're going to have y minus 2 equals 2 times 0.1. Now a tenth of 2 is just going to be 0.2. So y minus 2 equals 0.2. And if we add 2 to both sides, we're going to get y equals 2.2. That's going to be our approximate value for f of negative 0.9. Now we should expect that, unless we have some pretty, we'll call it a misbehaving function in that something that it would have a vastly different value around a given point. Unless you have something like that, we can expect that this value is going to be pretty close, or at least reasonably close, to the value at -1. And really I should, change that to a approximately equal. There we go. Okay, part B. Find the solution y equals f of x to the given differential equation, and it's the same differential equation from before with the same initial condition. So here we're actually trying to find the equation for y. Before, we didn't even know the equation for y, but we were able to approximate values right outside, right around this particular given value. But now we're going to find the actual equation for y and do something, hopefully a little interesting with it. So let's find that equation for y. I'm going to just rewrite the original equation here because what we want to do is try to separate the y's from the x's, just like we've done in a bunch of these previous separable problems. So looking at this, it's not going to be as easy as it usually is as far as just trying to use the cross products property and cross multiply. We're going to have to move things around a little bit more than that. We can start with that cross products property just to kind of get things going here. So 2 dy is equal to negative xy squared dx, but we still have that y squared on the right-hand side. So we're going to need to divide by that. Now dividing by y squared is equivalent to multiplying by y to the negative 2. This little expression, 2 times y to the negative 2, is the same thing as 2 over y squared. It's just going to work out a little nicer for us when we go to find the antiderivatives. Equals negative x dx. Now we want to integrate. And using the power rule, the integral of 2y to the negative 2 is going to be 2 y to the negative 1. And then we're going to divide by negative 1. So this is actually going to be negative 2 y to the negative 1. And on the right-hand side, the integral of negative x, once again using that anti-power rule, is negative x squared. And then we need to divide by 2, so negative 1/2 x squared. Now, both of these should have a plus c, but we're going to get to it. We're at a point now where we can just kind of move past that and just combine those c's right away. We're trying to isolate y here, so the next thing we're going to do is divide everything by negative 2, and so I'll get y to the negative 1 equals negative, or actually a negative divided by a negative is going to be positive, so negative 1/2 divided by negative 2 is going to be 1/4 x squared, and then c times a constant, or divide by a constant, or add a constant. Really, any time you're combining constants, your result is just going to be a constant. So we still have some plus c. Now, the last thing to do here is get rid of that power of a negative 1. And, that might be something that you don't do very often. So one way to think about this is like if, let's say we had, square root of y, and we want to, we have something over here, and we're trying to get rid of that square root. So what do? We square both sides. And the reason why we square both sides is because the square root of y is actually y to the 1/2. And to get rid of that 1/2, what we really want to do is like change that to a 1. So we take advantage of this power to a power property, which states that anytime you raise a power to a power, you multiply the powers. And if we multiply 1/2 by 2, you know what we get? We get 1. And so that's why we square both sides to get rid of that square root. So basically what I'm trying to get at here is when you have y to the negative 1 and you're trying to get rid of that negative 1, I want you to think the same sort of thing here, which is what can I raise this to get rid of that negative 1? I want it to be just 1 because I just want y. I'm trying to isolate y. So a power or an exponent that I can raise this to would be actually, surprisingly, negative 1. Negative 1 times negative 1 is 1, so you get y to the 1. You get that negative 1 to cancel out, and then you'll just have everything over to the right raised to the negative 1 as well. Basically what we're doing is we're reciprocating both sides, and we're not writing these expressions as rational functions or as big fractions here. So it's maybe not so obvious that we're just basically reciprocating both sides by doing that. But that is what's happening when we raise both to the power of -1. So yeah, if we raise both sides to the power of -1, we're going to end up with y equals 1/4 x squared plus c, all raised to the -1. So we've got our general solution for y, but we want to find the particular solution where f of x intersects this coordinate -1, 2. So in other words, we got to find c by plugging in the x and the y found here. So substituting those values in here, 2 for y and -1 for x, we get 2 equals 1/4 times -1 squared plus c to the -1. At this point, I can sort of unreciprocate what I just did earlier, which is to raise both sides to the -1 to get rid of that -1 power. And so 2 to the -1 is just 1 divided by 2. It's just 1/2. But really, what I'm doing here is 2 to the -1 to get there. And that equals 1/4 times -1 squared is just times 1, so that's just 1/4 plus c. Now I can subtract 1/4 from both sides. 1/2 minus 1/4 is just going to be a fourth. So that means c is 1/4. So now I can write my final answer here. Y equals 1/4 x squared plus 1/4 to the power -1. You could also write this as like 1 over. So if this happened to be like a multiple choice question, you might see the answer written as like 1 over 1/4 x squared plus 1/4. I kind of doubt that they would do that, but that would be equivalent. So just make sure that you are fully aware of what that raised to the -1st power actually means. Okay, so just getting a little bit more practice in today with solving these separable differential equations. But I want to give you a little preview of something that we're going to be working on in the near future, and that's slope fields. And so part C says, on the axis provided, sketch a slope field for the given differential equation. This is the same differential equation we've been working with, right? We found a linear approximation near x equals -1. And we also found an explicit formula for y. So in other words, we found this equation which has a slope that's given by this equation up here. That's really what a differential equation is. It's just an equation that gives you the slope. So another way of thinking about it is it's the slope equation. It's the m in the y equals mx plus b. So let's just talk briefly about what exactly is a slope field. Now, a slope field is just a way of representing all the solutions to a differential equation. And so what I mean by that is, let's say we have a differential equation, dy dx. Okay, in other words, we have an equation for the slope, and we say that, hey, the slope is 2x. Say, okay, well, if the slope is 2x, then what is the equation that has this slope? So, okay, well, what's the equation that has the slope of 2x? Well, we know how to anti-differentiate that. It's going to be x squared, and then 2 divided by 2 would just be 1. So y would be x squared. But it's not just x squared, because when we anti-differentiate, when we integrate both sides to actually find that equation, we do have that at plus c, because not only does x squared have a slope of 2x, but x squared plus 1 has a slope of 2x, x squared plus 2 has a slope of 2x, and so on, right? Because when you differentiate a constant, it becomes 0. If you work backwards from the slope to the actual equation, you're going to have this sort of unknown constant there. And so what a slope field is a way of kind of graphing all of the potential solutions here. So let's say we wanted to graph all the solutions of dy dx equals 2x. Well, the solutions there would be all equations that would fit this, this function, y equals x squared plus c. So somehow we'd have to graph like y equals x squared plus 0, y equals x squared plus 1, y equals x squared plus 2, and so on, even with x squared plus negatives. Now, I'm not really doing a very good job sketching this out because I'm just kind of trying to do it quickly. But if we want a way to kind of show what the graphs of all the solutions are. Because sometimes, most of the time they're not going to be as simple as just x squared. Sometimes they're going to be kind of, more crazy like this. We're not going to know exactly what it looks like just, by memory. Creating a slope field is a way to kind of construct what all those solutions are going to look like. So let me kind of break down how you find the slope field and how it should look. So it says sketch a slope field for the differential equation at the 12 points indicated. So notice we have a graph here, and we've got a total of 12 points highlighted on the grid. In a slope field, all we do is come up with the slope at each of these individual points. So typically at like 1, 1, 2, 2, but depending on your scale, it might be a little different. But most of the time, it's just going to be all the integers. And you're going to come up with what the slope of that function is going to be. Not the differential equation itself, but all the solutions of the differential equation. In other words, all the y equals and then with the plus c. So all this time that we've been looking at separable differential equations, we've been finding particular solutions, like we've actually figured out what the c was given a particular point was on the original function. But if we didn't have that given point, if we're just looking for the general solution, in other words, all the solutions to that differential, if we're looking for all of them, this is a way that we can show all those on a graph. So anyway, let's see what this would actually look like. And then maybe it might be worth kind of comparing what we're going to show here with what the graphs actually look like on, say, Desmos. So yeah, let's plot out. Basically, what we have to do here is we're going to find all the slopes at these 12 points. Okay, so we're going to plug. Let's write out exactly what we're going to do here. We're going to plug in each point to find the slope at that point. Okay, then we're going to sketch a little sloped line to match the slope that we found. Okay, so if you have 12 points here, let's kind of just break down where these points are. So starting with the top left, that's going to be -1, 2, right? I'm just going to take a moment here and write down all these 12 points. So -1, 2, -1, 1, -1, 0, 0, 2, 0, 1, 0, 0, 1, 2, and so on and so on. You don't need to hear me read off all these. Hopefully you're seeing the pattern here. Now, just know that like on any test I give you, quiz, or on the AP test itself, you don't actually have to show all the work here. And your sketch doesn't have to be perfect. We're just trying to get a general shape of what is going on at these particular points for the different solutions that exist on this differential equation. So in other words, like most of these, like once you kind of get going and understand what we're doing here, you can kind of calculate these in your head. You don't actually have to show like what each one equals. It's okay to just do it in your head and draw a little quick sketch. But I'm going to show all the work just so you can kind of see what should be going through your head as you're working through this. So we'll start with -1, 2. We're just going to plug that in up here. Okay, and hopefully we start to see like some patterns here that come out. So if I plug in -1 to x, I'm going to have -1. That's going to be +1 times 2 squared. 2 squared is 4. So we've got 4 divided by 2. That's going to be 2. All right, so I'm just going to say, just try to be brief here. I'm going to just say m is 2. The slope is 2. So it's going to look like this. At -1, 1, we get -1, that's +1, times 1 squared, that's just 1. 1 divided by 2 is 1/2. It's going to be sloped a little bit more like this. Just remember, like, slope of 1 is going to be like your 45-degree angle mark. Okay, so just to give yourself some kind of anchor or reference point for how steep these should be. Again, don't worry about it being super accurate. We're just trying to get the general idea down. Now, if I plug in -1, 0, I'm going to get -1 again, but that's 1 times 0 over 2 is just going to be 0. At 0, 2, we've got, we've got 0 times anything is going to be 0. So 0 divided by 2 is just going to be 0. So I'm going to draw a little line here that has a slope of 0. Okay, if I plug in 0, 1, again, I'm going to get 0 times whatever. So you can kind of see like how you can start to go a little faster here. Once you start plugging in kind of the same numbers over and over again, you're going to start noticing patterns and be able to move along like a little faster. So like if I plug in 0, obviously this is just going to be 0. So we've got a slope of 0 down here at the origin. At 1, 2, it's going to be -1 times 4 is -4. Divided by 2 is -2. If we plug in 1, 1, that's going to be -1 times 1 is -1. So -1 divided by 2 is -1/2. And we're seeing a little bit of symmetry starting to pop up here. If we plug in 1, 0, we're going to get 0 over 2. So that's just going to be 0. And then finally, if we plug in 2, 2, we're going to get -2 times 2 squared. That's going to be -2 times 4 is -8. Divided by 2 is -4. So that's going to be pretty steep there. So I'm going to just kind of do my best here to make this like as steep as possible without making it look vertical. At 2, 1, we've got -2 times 1 is -2. Divided by 2 is -1. -1, by the way, is that kind of other 45-degree angle mark there, or 135 if you want to talk about it in standard form. So at 2, 0, we've got -2. Okay, that's just going to be times 0, so that's going to be a slope of 0. And that's what a slope field is. Now, maybe I should take a minute here and open up Desmos and just kind of show you, and actually pull this up. So let's put in this equation. And we know what the actual equation for y is. It's y equals, the one we got in part B was 1/4 x squared plus 1/4 all to the power of -1. So you get like this kind of weird looking function. But that 1/4 right here was actually like what our particular solution was for that situation where we had that point. Let me see, what was that again? -1, 2. And we can see -1, 2, obviously on this curve. That's kind of how we set that up, right? So we're given that -1, 2 was on the curve, and that's what allowed us to find the c. So, but let's just say it was just any c. It wasn't 1/4. It was just plus some constant. And let's add a slider here. We can default it at 0.25. So we have that same function that we had in part B. And so, but we can change this value, right? We can change what this is. We're going to add that slider back. And we can change, we're seeing all these different functions. Right? Ooh, we get some, look at that. Oh, it's almost like you're seeing like a bubble kind of explode into infinity and pop out the other direction. How cool is that? Always love seeing how the geometry changes with the change in C here. Okay, so anyway, what we have graphed here is on the slope field. Let me change, give me a second here. Let's change our window to go from -1 to 2, and our y-axis, so we see exactly what we're seeing on the slope field, from -1 to 2. Okay, so this is exactly what we're seeing, and maybe I'll zoom out just a little bit. Really just looking at like this top section here. But look at the slopes, just look at what you have drawn there compared to all the graphs that I'm seeing as I switch out, change my C value. I'm actually going to bring these out way more than just 10 to negative 10 to 10. Let's go negative 100 to 100 and see if we can see just a lot more about what's happening here. Okay, so notice, let's see, let's get this is going to change. Maybe we don't want to go that much. Let's go like maybe negative 20 to 20, because that is just changing way too much as I drag it along. Okay, this is better. Okay, so watch, so like getting close to 20, see how the slopes down here are real close to 0, okay? And we see that happening on the slope field. And as the C value changes, as we hit so look at when y is 1, for instance. So I'm going to hit that right about there. So notice here, we do have a horizontal slope. Notice that 1 comma 1. Now this graph does not pass to that point, but if we modify the C value so that we pass through that point, like right about, it jumps so fast. It's going to be like in between 0.8 and 0.7. I wonder if we can do like 0.75 here and get real close. And so take a close look. This is a 1, 1, what that slope looks like there. And it should be pretty darn close to a slope of negative 1/2, which is what we calculated. And it does kind of look like that, right? Like if I just look at from here to here, it does look like I'm going down. Well, probably the easiest way to look at this is like right around here and kind of see, it does look like it's going like down 1/2, right? So we can kind of see that, yeah, in fact, the slope right around here is at negative 1/2. And now let's change this a little bit more just to look at one other point. Let's take a look at that 2, 2 point. Now 2, 2 is going to be way over here. Let me zoom over here. We're going to have to modify the C value a little bit more to make it actually pass through that point. And so like the slope is not going to be -4 unless we actually hit that point. That's going to be between negative, looks like 0.5, 0.6. Let's try negative 5.5 and see if we can't. Oh, maybe negative 0.5 actually hits it pretty good. So that might actually be a perfect fit there. And we see at this, when the curve actually passes through that point, the slope there is going down 4/1 roughly. It's curving, so it's always changing. But right around here, right there, actually, it should be exactly negative 4. It's going down 4/1. So all these solutions that we're seeing, right? Even though these graphs look kind of wildly different for different values, right? Are all being simultaneously mapped onto that slope field. And that is basically what a slope field is it shows you, at least it gives you a graphic like representation of all the solutions to a particular, or not to a particular, but to a given differential equation. All right, that's enough on that. I think I kind of beat that horse, right? So let's move on to number 4. Now that we have a little bit better idea about what we're looking at here, it says select the differential equation that matches the given slope field. So here we're kind of working backwards. Instead of being given a differential equation and being asked to create a slope field, what we're doing is we're given a slope field, and we're going to have to come up with an equation. Now, the thing here is, for these multiple choice questions, is you don't actually have to come up with the slope field algebraically. So we're not really going to focus on that for this particular problem. Instead, what we're going to do is just kind of do process of elimination here to figure out like which one actually works. So there's really 2 ways you can kind of approach this. One is to kind of look for patterns that you might notice. You could always potentially solve these equations for y. We might investigate that a little bit, but so that's one thing you can do is kind of look at the graph and look for patterns. Like for instance, see how everything's undefined along the y-axis, right? We got all those slopes are vertical there. That means that when x is 0, the slope has to be undefined, and the only way to be undefined is going to be to have like a divide by 0 error. So that means when x is 0, we've got to have a divide by 0 error. And we see that here, not here, so we can eliminate that one. And we got here. So that's what I mean by look for patterns and see if you can't eliminate any based on what you're seeing. So yeah, that's one strategy. I'm going to kind of just write these out. Okay, look for patterns. Okay, like for example, we see that when x is 0, the slope is always undefined. Similarly, we see that when y is 1, the slope is always 0. So when y is 1, the slope is always 0. Okay, so if I'm looking at these different choices, in order for these fractions to equal 0, I'm going to need the numerator to be 0. And so which ones are going to equal 0 when y is 1? Oh, sorry, not when y is 1, when y is negative 1. Yeah. Okay. Yeah, this makes a little bit more sense. I was going, kind of scanning through the answer choices and thinking, none of these are going to be 0. So yeah, so we can see that there's quite a few actually that if I plug in negative 1 for y, like this one, this one, this one, all those are going to have a numerator 0 when y is negative 1. So we really don't actually get to eliminate any other ones based on that. But that's what I mean by looking for patterns. There's other patterns that you can look for as well. Kind of seeing almost like a quadratic thing going on there. That's one thing you could do is like sort of try to connect the slopes to the best of your ability. Sometimes that's kind of hard to do, but you've got something going here. It kind of looks like maybe we've got some asymptotes, some asymptotic behavior. But another strategy that you could use is to actually just plug in points. Okay, so for example, like we're looking at, we already kind of decoded what's going on with those horizontal and vertical lines. But if I'm looking at anything else, let's say I want to know, what kind of slope should I be expecting at, say, like 1, 0. Okay, what's the slope here? Slope here, it looks like it's like kind of like a 45-degree angle line there. It may not be. It might be, approximately, but we can say that it should be approximately 1. Okay, if not exactly 1. So if I plug in 1, 0, I'm looking for this to either be 1 or at least like something reasonably close to 1. And if it's something way off, then I can eliminate that as an answer choice. So like if we look at choice A and I plug in 1, 0 into x, y, so 1, 0, what that gives me is 1 over 1, which is 1. Okay, so yeah, that could be A. Going over to B, if I plug in 1, 0, I'm going to get 0 plus 1 over 1 squared. Okay, that could be 1 also. That doesn't really get me anywhere closer here, but maybe I'll have some more luck with D here. So if I plug in 1, 0 here, I get 0 plus 1 squared over 1 squared. That's going to be negative 1 over 1. This is negative 1. That is incorrect. So I am able to eliminate an answer choice that way. So we know it's definitely not C. It's definitely not D. It's going to be down to A and B. All right, so let's maybe pick another point and kind of just do the same thing with A and B and see where that leads us. So maybe we go a little bit further off here. I'm looking for kind of another point where I'm expecting it to be 1, and I'm seeing another one over here, kind of 4, 1, maybe 5, 1. But 4, 1 kind of looks the same here. This should be approximately 1 here. So we're gonna test 4, 1. Whereas over here we tested 1, 0. Let's test 4, 1, see what happens. So with choice A, we have 4 plus 1. That's going to be, no. 1 plus 1, sorry, is going to be 2. 2 squared is 4. So we get 4 over 4. That does equal 1. That seems to check out. And if I plug in 4, 1 to this choice B, I get 1 plus 1 is 2 over 4 squared is 16. Okay, 1/8. That is not anywhere close to 1/8. Up 1/8, that's going to be like practically horizontal. So yeah, it can't be B either. And by process of elimination, we can identify that as being A. Okay, so those are just kind of two strategies that you can use to solve a question like this. These slope field questions can be a little tricky. But one last thing before we're done for today is I want us to sketch the solution curve that passes through the point 3, comma 1. So it passes through the point 3, comma 1. We know for certain that the slope is going to be approximately right there, and 3 comma 1. And so what we're being asked to do is to basically sketch the curve that passes through that point. There's a couple different ways that we can approach this. One way, if you just really want to be super technical about it, and honestly, I don't think you need to go through the trouble on this kind of a question. But what you could do is, now that we know what the answer is, choice A, is you could solve for y here like we have in the other separable differential equations, and just plot that graph. But what I like to do is just kind of follow the slopes, kind of how they're being plotted out, and almost like you're kind of like moving along the current, like if you're like floating in the ocean, and each of these slopes represent like a vector of velocity pushing in a certain direction, and just kind of follow it how the direction it kind of shows you to go. So like, I know like part of my graph's going to look like this, and then it looks like as I cross over the x-axis, I should be kind of horizontally out, getting more and more flat, and then like as I move over to negative x values, it's kind of going back up. I do see like some decent symmetry here. So I kind of want to maintain that symmetry and do something basically like this. And you get a graph that does look like a parabola. And I'm not going to go through the algebra here because we've done already so many of these. But if you want to solve for y, you can figure out exactly what it is. But the AP test is timed. So if you can save a little bit of time and just like use your intuition, you can get a pretty good, decent sketch there, or at least if it was a multiple choice question, should be able to answer something like this. So there's really no work that I'm going to state there. Hopefully my explanation was sufficient. If you're still really confused about these slope fields, don't be too scared. We are going to talk about these more in our next lesson. I'm not gonna let this lie where it is now. Thanks for watching, y'all. Have a great day. I'll see you next time.